All right, welcome back. We are Game 2005. That's Game Physics in the Fall 2020 semester, and it's Lesson 1. And I am your instructor for this semester. You should mostly know me. Most of you should know me by now. My name is Tom. I've been teaching technology since 2011. My background is in software engineering and game development, and I consider myself, this is a new thing, a polyglot programmer, which means I can program in many languages. Yay! That's a fancy thing. I gotta give myself a title. Anyways, the coolest thing I've ever made is an asymmetrical multiplayer VR game, Manos Returns. It was a lot of fun to make that game. My favorite game is Dungeons and Dragons, the tabletop role-playing game that I played today, and I play every Friday, every other Friday. And my current project is I'm kind of pursuing a master's in VR security and machine learning, where we do, I'm kind of exploring four-factor authentication for VR, right? So it's very interesting for me, and it's something that I've been working on over the last 6 months. This semester, I'm not going to be doing physics alone. I have a colleague of mine. His name is Spencer Poon Woo. He is going to be your lab instructor. And if you notice this semester, we canceled the first labs, and the reason for this is because the lab came before our lecture this first week, and also Spencer was kind of brought on kind of later on in the process. There was supposed to be another instructor, but I'm really super excited to introduce Spencer. I know he's not here right now. He's going to probably come on later on, but Spencer comes with a wealth of information. He's actually working in the game development industry. He's worked on several games, and when he comes along later on, maybe he can talk to it as well. But he's currently the senior game developer at something called Prodigy Education, right? Where he's creating features and maintaining systems on a massively online role-playing game with over 90 million registered users. So it's really awesome that he's joined us this semester. I'm super excited to work with him. And his coolest thing he's ever made is a procedural dungeon generator in 2 weeks. That's pretty awesome. His favorite game is Breath of the Wild. You can talk to him about that. And his current project that he's working on is this server authoritative battle system, I guess, for the game that he's working on at Prodigy Education. So really, really cool. Really excited to have Spencer working with us this semester. And he's going to be working on the labs, the C++ and STL stuff with you guys this semester. And I have a question from Hardik saying, will he record the labs as well? I'm not sure. I'll talk to him about it, but he's going to kind of go through his process. I think there might be something synchronous that he has with you guys, so you guys can do things together. But I'll definitely work with him. If that's what you want, just let him know. He's a pretty cool guy, and he usually he wants to provide a really good experience. So again, super happy to have him. The next one is this schedule. So I wanted to share the outline with you. This has changed over the years, and this is something new that we're doing. Typically what we do in physics is we also include a calculus portion. And if you talk to some of the students in later years, years 2 and 3, as an example, you guys are just starting in year 2, but anyone who's in maybe the last part of year 2, just from a collective perspective, or year 3, or a graduate, they would have told you that whenever I did the physics with them, it was with calculus. I got to tell you that I have never seen a student over the course of the years I've been teaching physics and calculus use calculus in their games. And I was always kind of discussing it with Alex and with Philip and with others that maybe we should take calculus out. And I think that's what we've done this semester. We've kind of said, look, you know what? Calculus is great, and if you want to dig into it, there's a ton of stuff if you're going to be an engineer with calculus, or if you're in university and you want to dig into the math, calculus is fantastic. But otherwise, I just don't see that there's a place for calculus in the world we live in right now for physics for games, at least right now. So that's why we've taken it out. Okay. I'm not going to suggest to you that calculus isn't important. It's just that it doesn't make any sense going forward. At least not in this program. All right, so then we're going to get into... So this week we're going to do a general geometry and trig review, because you can't really do physics without geometry and trig, and you guys should already have had that last semester or the semester before. But we're going to just touch upon it really quickly, things that you should know. I'm going to talk about things that you should know this semester. And then we're going to get right into physics next week. And again, this is different than what we had before. In the past, we would have 2 weeks or 3 weeks actually, of calculus, and then a test. We've gone away from that. So next week, you're going to get into motion in one direction, which is kind of like simple motion. And you're going to get an assignment number 1. The assignments are going to be small groups, 2 to 3 members. I'm going to allow. I'm not going to allow bigger groups than 3, so please don't ask when we come to the assignment portions. You're going to select your partners. You can switch your partners every time we have a new assignment, but you must keep the same partner for the assignment portion when you start. You're going to kind of align who your partners are. The questions I always get asked are, can I do my assignment alone? And this semester, the answer is going to be no. You need to pick at least one person to do your assignment with, assignment number 1, 2, 3, and 4 throughout the semester. All right, so it's going to be pair programming at the very minimum. So please don't ask to work on your own. Okay, if you need someone to work with, I will assign you. For partners who don't work out or who don't produce, they're going to get a 0. So it's kind of like you're doing it on your own anyway. And we'll talk about that. But I prefer that you guys should know each other by now. You know who works okay, and I'd like you to try and arrange to work with somebody else that you know is going to do okay. Okay, so that's motion in one direction, and then that's like only on one axis, on the x-axis or on the y-axis. We can talk about motion about this, and there's a whole lecture devoted to that next week. Then we're going to be talking about motion in 2 directions. So x and y motion, and there's different equations that go into come into being for both those 2 scenarios, right? Then we're going to get into Newton's laws of motion, circular motion, energy of a system, and then finally in the second half of the semester, projectile motion. We're going to do kind of a case study on projectile motion, which is week 9. Okay, so most of the physics pieces are going to be happening before mid-semester. There is going to be a mid-semester test, and we're going to talk about the evaluation scheme in a second, which is going to be theoretical. Okay, so that's going to be a true-false multiple-choice test, individual. All right, and you'll have the whole week to get it done. Just as I've run my tests in the past, you'll get it on a Monday. You'll have until the Friday to get it done. Okay, so that's your midterm test, and it'll be different this semester because it'll include questions from the different PowerPoints. It's open book, of course, and it's probably going to be all inclusive up until week 7. It means anything we talk about today and up until week 6 will be included. Notice there is no class scheduled on week 7, right? And why? Because there's going to be some kind of lab work, and also I'm going to be helping you guys with your assignments. I've scheduled the assignment 2 to be due on the 6th week, which is around October 15th. But I always tend to move that assignment out 1. It doesn't matter what kind of assignment we have, and this will be a new assignment this semester where it's a programming assignment more than anything else. I want to give us a chance. So if anything, on week 7, we'll just have office hours instead of an actual class. You can also use week 7's time together, at least from a lecture perspective, to again, do your test where I can kind of go there, supervise, answer questions, all that kind of stuff. But typically what I'm going to do for week 7 as well as week 15 is those 2 weeks I'm going to reserve for office hours, for things like an assignment that didn't go so good and you want me to talk about stuff, or you have a problem with the current assignment, or you need help with something. I'm going to have office hours during those times. Okay? So there won't be formal lecture on week 7s and week 15. But there will be possibly labs during those weeks, and that'll be up to Spencer. Spencer is going to kind of go through with you guys, and he's going to have a different lab schedule than me, and he's going to be more specific about what he's going to be talking about in the lab, but mostly related to what I talked about the previous week. So example, if I talk about geometry and trig this week, then chances are there might be something about geometry and trig in his lab from a programming perspective next week. All right, so he's going to have us on Tuesday. All right, so that's how it works. And people are asking about recording. I absolutely it's working. And if you look up on Blackboard, there is a link already on Blackboard. If you want to watch me in slower time, you can go to this link on Blackboard, and this is your YouTube link. You can get closed captioning here in real time or near real time. It's not so bad. And if you're someone who's not a native speaker, highly recommend maybe you want to watch it on YouTube as opposed to being on just on Zoom. Okay. Back to this. So that's the first half for the most part. And then in the second half, it's going to be different kinds of collision detection. So we're going to start off with 2D collisions and optimizations around that. So more type of collision shapes is what you're going to have. And how to optimize, collision detection from a 2D perspective. And then the next week is collision response. So sure, you collide, but what about this dynamic collision stuff that can happen? What about when there's two objects that are, kind of rushing around in real time? How do you do that? What happens with the tunneling effect of bullets? How can you, figure that out? What do you do for those kinds of things? So we're going to be talking about that kind of stuff around a week 11. Now, this is the new stuff that's come in because you guys are also taking OpenGL this year, yeah? And I think you are taking OpenGL. If you come up with yes, I can see that I'm right. So in the second half, Alex and I are working it out so that you'll be using OpenGL in the second half from week 12 on for physics. So what you're going to be doing is 3D collisions, and Spencer is going to help you kind of work out. I'm not sure if we're going to use the SDL framework as the assignment framework, with just an OpenGL context for a windowing system, or if we're going to give you something like GLFW or something else, or we will allow different things. We're going to have to talk about it as we come forward because assignment 4 will be done in 3D. There'll be some kind of assignment in 3D that you'll get. And it'll be with 3D collisions and 3D collision response. So like how do you bounce off of a 3D object we're using OpenGL. So that's something that we're going to be looking at for the second half near the last part of the semester. Okay, so I think I'm super excited to see what you come up with on that one. I think it's the new part. And then in week 14, we're going to have a special topic where we talk about particle systems and how to create them. Okay, so that's something that we're going to be working on. Assignment 3 may have an option to create a particle system editor where you make your own particle system editor that you can use in your games. So we're going to be talking about that when we formulate assignment 4. It has not been created yet. I'm waiting for. I want to connect with, with Alex to make sure that it's well balanced as well as works within, with the other course that you're taking. So again, I want to try and create, like always, some kind of interconnectivity between courses so that, you kind of kill two birds with one stone. And I think it's a good thing for you guys, as opposed to my course is the capsule, Alex's course is a capsule, and who cares, we're going to just kill you guys with assignments. I prefer not to do that, right? I prefer that I can work with Alex, and maybe something that he comes up with can also work for me. Maxim says, how much time did it take to go over calculus last time? Usually 2 to 3 weeks. And in 2 to 3 weeks, I covered all of high school calculus. I'm talking about like grade 11 and grade 12. Why? Because we only had 2 weeks to talk about everything that you needed for the game. And of course, I couldn't possibly cover everything. And actually, it's really few. It's not a lot for calculus, especially the more advanced stuff. So that's why we decided to take it out, Maxim, because there's just too much. Okay, so let's get into our evaluation. From an evaluation perspective, you're also going to have some labs. So, being in lab with Spencer is a good thing. Why? Because there's going to be a lab mark that he's going to be responsible for producing for you every week. So every time you get together with him, there'll be some kind of lab exercise that you're going to have to submit, and something related to what we talked about in lecture the week before, typically. Now, there's one extra lab that we're going to probably produce, and the reason for this is because we owe you a lab. You missed a lab this week, so chances are we're going to have an extra lab, and Alex and I are going to plan something like that probably in the second half of semester when we have an extra lab come in. Okay? So that's happening, and you need to do 10 out of the 12 labs to get your 10%, okay? Assignment 1 and 2, notice that they're relating to simple motion. Assignments about simple motion and 2D motion, they're worth 10% each, so a smaller amount in the first half. In the second half, you'll be getting 2D collisions, so a little bit of a meatier assignment, right? Meatier as in like more meat to it, with collision detection and response, worth 15%. And then, again, more meat, kind of higher weighted assignment with the 3D collisions one, which is going to incorporate things like your OpenGL framework and 3D collision and response. So that's happening with the last assignment. So again, you can see that the assignments are worth collectively, so there's 30% and 20, that's 50% of your total grade in the course, right? There's a midterm test that you're going to do that's individual. And there's a final practical test that's also individual. Okay, so it's not you're not gonna do this alone. You're gonna do it alone. You're not gonna do it with anybody else. So that's why it's best that you get into the coding piece as much as possible with your partners. I recommend a good sized team is a team of 2. Okay, and the reason why I'm saying that is because pair programming is easier because it's pair programming, 2 people. I will allow up to 3 if you have a good reason to do so. In other words, like, let's say, for example, you really want to put a lot more into your particular assignment, or from a work-life balance, school-life balance perspective, you just need, you're going to do less, but I will allow it, up to 3 people. Beyond 3 people, these assignments, they're too small, right? So you won't get, I don't believe you'll get enough out of them if they're more than 3 people on these assignments. So let's keep it small. I highly recommend 2 people, and 2 people is the minimum, and 2 people is probably the right number for you guys for each of the groups. But your final practical test is going to be alone. So if in your assignment 1, 2, 3, 4, you really didn't do anything and you're skating, then when it comes to your final practical test, you're going to get squashed, because it's going to include some of the stuff that we talked about. It could be 3D. It could be some more complicated 2D thing that I'm asking you to do, and you'll have the entire week to get it done. And that's why when you look at the schedule, there's no lecture plan for that time, so that I can help you, with any kind of issues surrounding your test, because it's a practical test you're doing. Okay? To be honest, I would like to do a practical test on midterm as well. But I find that you need to know some theory about the stuff that we're doing, and that's why I want to test you on the theory. Having a chance to go through some of the PowerPoints again and kind of revisit the concepts, it's important to understand those things, and that's why there's going to be a test on theory more than anything else. Okay. Oh yeah. I got to also talk about this. This is new for this semester, and I kind of got you guys, some of you, to do it last semester. So the people that had me in the summer semester for AI and so on, you experienced it for yourself. We did assignment videos, and we're going to do it again this semester. Is the time limit on the final still 2 hours after we start, or is it all week? It's all week, Kira. I'm not going to kill you guys with a 2-hour final. That's crazy, right? This way you have a chance to absorb the material, and I'm going to give you a task to do in the beginning of the week, and you have until the end of the week to do it. Sometimes it's a curse, and sometimes it's a blessing. And the reason why it's a curse sometimes is people are they procrastinate. Okay, don't, your videos were great, Max, and what are you talking about? So to me, I liked your videos. But going back to this, assignment videos are required this semester. So you and your team, when you're submitting a video or submitting your assignment, I will not accept assignments without a video this semester. All right, so that means that you must create a little short video, and I'll talk about what needs to be in there. It's going to be I only want to record your screen and your work. We're going to talk about what's required here, and you're going to put it up either on YouTube or Twitch. I want to click on the link and make it work like that, and you're going to upload the link to Blackboard along with, most likely, your assignment archive, a zip archive of your assignment, and a GitHub link. Those 2 things, or all those 3 things, are mostly going to be required. So details for each assignment will be released each week for this one, so that way if I have each week that they're due, and that's part of what we're doing. So again, things that you're going to include in your assignment. You must include a short PowerPoint or Google Slides slide deck that includes a single slide to start your video. Right? So like one slide, a title slide, call it what you want, right? And that title slide that you're going to submit is going to have a current image of you and your partner. No avatars, no cats allowed, none of that stuff. It's going to just be you. Okay, let me take that back. If you want to add a cat, that you're holding a cat when you're in the title slide, I'm okay with that, but I got to see your face, all right? I got to see most of your face. How about that? All right, so I want to make sure, so you can still be creative. A dog is okay too, if you have a dog. So again, it's going to be displayed on the page. You're also going to include your full names, your student IDs, your course code, your course name, and your assignment information. And then each group member will be required to present some portion of your assignment. So it's not just going to be the best presenter, because this is not game production. This is you talking about your application, right? So you're going to make a little application at the end, right, of your assignment. Every assignment is going to have something that you're going to show. And what I want you to do is switch between you and the other group member. Now, how do you do that when you're remote? You guys are in different places. There's many ways to record stuff. You can smash things together and make one recording. It doesn't matter to me how you put it together. It does not have to be a professional recording. As long as I can clearly hear you and clearly see your screen, and that you've managed to show me your functionality for your app, as well as demonstrate what your code does. In other words, explain your code. Go through the code and go, so here is my collision detection code as an example, and you can see here that I'm clearly using a capsule collider. When I'm between two objects on the platform as an example. All right, and this is how the capsule collider works. Here's the math, kind of stuff. If you can explain that, then I'm good to go. It doesn't matter. As long as I can hear you and see your screen, you're good to go. All right. So that is, the video requirements. You need to be clearly heard, and you need to be clearly the screen needs to be clearly visible. I do not need at all to see your face live, like a floating head or anything like that in the video. You don't need to do that. If you want to do that for fun, that's up to you. But I do not need that. And please do not use your phone to record yourself, demonstrating the video on your computer. That's not going to suffice. I want to see a screen recording, not a recording of you. Okay, so please don't do that. The other thing is that the video shouldn't run more than about 5 minutes, give or take, plus or minus. It could be less. If you can knock it off in less minutes than 5, great. But beyond 5 minutes, please guys, don't go too crazy with more than 5 minutes of video. Because remember, I have to go through that stuff, and so does Spencer, and it's going to take a lot longer time if the videos are very long. Okay, so 5 minutes max is the rule. Now, some people have asked me in other courses that I presented this almost identical slide. They said, do I have to do it in this order? Do I have to demonstrate first and then, kind of explain my code? And the answer is no. You can do it in any order you want, as long as it meets my requirements. Show me your code somewhere, how it works, and show me your demo. Show me that it works, that you don't have errors. If your code doesn't work, or if your application is not buildable or workable, you need to show me that too. You say, you know what, here's my application, it doesn't work. Say it, right? And these are the features that I missed. Also, what I want you to do is talk about any kind of extra features or optional features you put in there. For example, I might have some optional bonus features. Talk about them. Say, maybe even put an extra slide in there for me and say, by the way, Tom, here's bonus features. Give me extra marks, kind of thing. And this way, I'll know to zero in and give you those extra marks, as opposed to, did they actually enter, extra features? Probably not. I don't know. And sometimes people are very skimpy on their presentation. Here's my game. Look, it collides, it shoots, and it does the thing that I want you to do. Okay, bye, Tom. And that's not good enough, right? Please, give yourself the time frame. Give yourself 5 minutes. One of the challenges people have is some of you are not native speakers, right? So, you are, as an example, English is not your first language, and some people are trepidatious. They're worried about how they're going to come across. The best way for this, in my opinion, is for you to script out a little bit of the thing that you're going to say. I know it takes a little bit of extra time, But then if you kind of read what you've written, or even use it as a guideline, like some kind of cue card equivalent, I think it's going to be better from a presentation perspective than if you just ad lib and try and talk to your stuff. It might, most times when we ad lib, things go a lot longer than if we have some kind of plan when we're talking. Okay? So that's the structure of the course. And at this time, I want to take any kind of questions you have about the course. You can come on the mic. Just be wary that I am recording things. So if you ask something, if you're brave, as an example, then you're going to be recorded on YouTube. If you're not brave, you can certainly post a question in chat. Okay, go ahead. And again, I'm taking questions. Any questions you have about the course outline or concerns or anything like that, please.
Hello.
Hi there.
You can hear me, okay. So if you're going to choose a group member, or if I ask you to choose one, do I email you, or, because I don't know anyone, so I'm definitely not going to partner with someone.
So Tam, are you new to the program, or?
No, I was in this course 2 years ago.
Okay.
There was a college strike, and I ended up dropping out.
I remember the college strike. Yes, I was part of that. So, and it was a terrible time, and I apologize that you went through that. But I'm glad that you're back. That's a really cool thing. So thank you.
It's perfect timing because now I live 3 hours away, so there's no option to come back.
Yeah, some people may disagree with you. They might say it's not a good time because everyone's remote because of Corona. But if there you go, Alexander Barnes there. He's saying he'd like to be your partner. So he's on chat.
Well, that solves that, I guess.
There you go. Thanks, Tam. Welcome back.
Thanks.
All right. The other thing is that Justin says he prefers in class, and I agree, Justin. I think that to me, I prefer in class too. I like seeing your faces. I like being with you guys. I like seeing the light come on, like I've talked about before. When you gonna get something, or even when you feel confused and you don't understand something, I can see those things, and I can't do that with Zoom. Even if you had a whole Brady Bunch kind of bunch of tiles everywhere in Zoom, I can't really tell if you're confused or not. There's just too many people at the same time. Like for right now, we have what looks like 85 participants, right? Which is a lot of people on our Zoom call, right? And again, what this means is that I just can't possibly get to everybody, kind of thing, and see how you guys are doing, right? So that's kind of an important thing. And so for me too, I think it's a challenge. So what do we do? How do we mitigate this from a communication perspective? Use Discord. And I've kind of, our old Discord server, I'm just going to pull up Discord for a second right now. And by the way, I'm also, I've created new Discord servers for the first years, so you can see that they're killing me with DMs today. But our old Discord server, which is GBC Game Programming, what I've done with this one is I've removed you guys from all of your old teams. And, most of you should be second year. Some of you might be other years, and it's totally fine. I've just separated us, kind of professors from the students. But please hit me on Discord. I think I'm better, and so is Spencer. Spencer's also on Discord. I'm going to include him in this server. He's not in here right now. But I think that as long as it's within a reasonable time frame, you guys can come, can communicate with me on Discord. I'm pretty responsive for the most part, as long as it's not something like every other Friday where I'm playing D&D. I may not respond as fast on those nights, especially since I don't just play D&D. Anyway, let's continue. But like I said, hit me up on those things from a communication perspective. One thing that I've also asked, I've also been asked lately is, why don't I just produce things live on Discord and not on YouTube, right? Because, Discord can handle, live broadcasts and stuff. I just feel sometimes that Discord cuts out from a sound perspective. And it really depends on the volume of people. I think it's okay for us to connect in a chat, but there's a limitation in terms of performance and fidelity that I find that I can't get on Discord yet, right? I know some people, sorry Herman, and I have to say, Herman, I used I told you I was going to use your game. I Herman is the famous guy that I talked about in the summer semester. I used his game as an example for all the other games that I wanted for AI. So Herman, thanks a lot. So that's the I hear you, Lisbeth. If you're always a DM and you're never a player, it's like always the bridegroom and never the bride kind of thing, and it's a challenge for me as well. I like to be both, and it's hard to to kind of switch in and out, especially when you're always the DM. Anyway, so let's focus on communicating together on a regular basis through Discord. I think that's going to be our primary communication channel. If you need to reach out with me and it's official, any official communications like I'm going to drop the course, Tom, or I'm really having a problem, Tom, I need more time on this, Tom, or that, Tom, then you need to communicate with me through official channels on Blackboard. Okay, so in other words, through George Brown, my George Brown email. All right, which is an ugly email. I don't like Tommy. I don't know why they picked that, but it works. Use that one. So like that, okay? And by the way, for people who are playing D&D, and I know that I'm digressing, but what the heck, since we're together, and I'm excited to see you guys again. It's my fault, okay? I'm excited, right? Go to Roll20. I think I use Roll20 a lot for Dungeons and Dragons. I think it's a great way. I don't endorse them or working with them, but I found this platform is pretty good for remote play, and we've been able to include players from all over the place just by using Roll20. So, I mean, it is a game development program, so what the heck. Anyways, getting back to what we're doing today, any other questions around our structure or schedule or things that we're doing?
Okay, Tom, I have one question. Did you hear me?
Yeah, I can hear you. Go ahead.
So I'm living in Ukraine, and some lessons would be at 1 a.m. or 2 a.m., so it wouldn't be so nice for me. So it's a question about some labs. Would it be posted on Blackboard to make it on the next day, or it would be processed through the lesson?
So, Andrew, to me, you know what? I think that I'm probably going to talk to Spencer about this, but I think my whole thought around the labs, it should be due in week. That's what I want. So, not necessarily in day. I mean, it'd be nice to get it done in day because I think it'll be just easier for you guys to get it done in day. But if you're remote and your time zone is different, and I know that Maxim, you're remote too, right? So, so between the two of you guys, I know that you're. I mean, it's probably way later over where you are right now than where I am, like 6 or 7 hours ahead or more. 11 hours difference. Thanks, Maxim. So that's a lot of difference. That's like 10 o'clock at night for you guys, 10:30 at night. So yeah, I don't want to keep you guys up late. So I will talk to Spencer about it, and hopefully, or if he comes on later on, and then we'll work it out. I don't think no one wants to be make your life difficult, Andrew. So that's not my intention. That's for sure. And I think Spencer's on the same page when it comes to that kind of stuff. So hang tight, and when you get together with Spencer next week, I'll have a communication with him before that, and he'll go through the schedule with you. Okay?
Okay.
All right. Any other questions related to our schedule before I get into the meat and bones of this thing today? And by the way, I want to say one more thing. Hi to all my friends that I missed, that I haven't seen in a whole semester. I didn't see you guys in the summer, and we saw each other very partially in the winter semester. And I miss you all. All right? So, it's been a long time, and I'm really super excited that a lot of you have made it back into the program. I know it's difficult. It's not the same as being in, in class, like some of you have said on the chat. And like I said, super happy that you guys are here and that you guys are continuing, and we're going to do this stuff together, guys. So hang in there. Let's make this a good semester. I know that Alex is super excited as well. I've talked to him about it. And yeah, Sam, you're one of my dynamic duo from a couple of semesters ago. So the other one is Kiara. You and Kiara worked really, really well together. So I'm hoping that you guys or someone like that, Vineet, and all the other people that have come back to the program. I'm super excited for you guys to be here, and lots of love for everybody out there, guys. And I'm going to say that and stop because I think I'm feeling the blues too. I think I'm feeling the way that some of us have felt, where we're disconnected, and I got to say that. And now that we're back together, we can do some good work and get some really great learning done. Physics is a fantastic subject. It makes our games awesome, and it gives us some really cool special effects. So let's get back into it.
Hey Tom, I just had a quick question. Can you hear me?
Yeah, sure.
So I was just wondering, you said that you didn't think calculus would be super beneficial, but like other areas of math, such as like discrete mathematics or like graph theory, would learning that independently be beneficial to like this course and program?
Eric, you know what? It's not that I don't think calculus will be beneficial. It's just the way we were offering calculus in 2 weeks that's not beneficial. I think also that calculus is great from a pre-testing perspective. If you want to, test out your formula and create an algorithm, calculus is fantastic to help you. All the other math that you take, math is, a programmer's best friend, right? So, yeah, I think like linear algebra, never forget that stuff. Vectors and, matrices and all that kind of stuff, especially this semester with 3D graphics, are going to be super important for you. So to your point, I think math, don't forget your math. And would you learn it on your own? Absolutely. Absolutely. You keep pursuing math. You should have don't forget math, because when we don't use math, we forget, right? So, yeah.
Awesome, thank you.
Thanks, Eric. All right, let's get into this.
Sorry, I have one question as well.
Okay, Justin, go.
The question is, when it comes to doing the assignment, since right now we're in our lecture, and you said we could do it in a pair or a group of 3.
Yep.
Are we allowed to do it with other people, like other sections? Because like the labs are in different schedules for everyone else, but
it doesn't matter to me.
Doesn't matter?
Yeah, because you're not going to be presenting it to me live. You're going to be recording a video, right? So if you can get together with the other people in other sections, and if they want you, right? That's the thing. Make sure you get together with people who want you to be a partner with them, and this is for everybody, right? Don't just like randomly group together. Then yeah, you can. I mean, it doesn't matter. It doesn't matter which block you're part of, for sure. It doesn't matter to me.
All right.
All right, let's move on, guys. I got to move on to the meat and bones of this today, and then hopefully maybe Spencer will come on, and I'm just searching through, and then he can kind of say kind of a hi bye to you guys as well. All right, so yeah, we're going into this geometry and trig review, and this is really exciting stuff for people who like geometry and trig, which I think is the basis for what we're going to be doing when it comes to moving at all on the screen. So let's talk about this. So we're going to cover things like really simple things like angles and triangles. Hell, if you don't know triangles and you're trying to do 3D graphics, good luck on that one, right? You need to know triangles really, really good. So we're going to just do a very high-level sweep of geometry and trig. And I've got some example questions in the back of this PowerPoint that you can use for practice. All right, so let's talk about that. So again, let's think about what geometry is, guys. And again, forgive me if you just did linear algebra and Math 101 in the last 2 semesters, but I guarantee you some students, what they do is this. They take their math and they're like, phew, done math, don't care about math now, right? And then they come into a physics course and they're like, yeah, there's math. And they're like, oh man, there's math again. Yeah, there's math. And we have to remember some of the key points. So that's what I'm going to go over, just the key points of trig and geometry. So geometry is all around shapes, space, and symmetry. Okay, and this section, what we're going to be looking at are things like angles and triangles. We're going to talk about that, and when it comes to that area, the area that represents angles and triangles is trigonometry. Okay, so without trig, it's difficult to calculate things like what the next pixel is going to be for your projectile. I'm firing a gun or some kind of projectile. I want to figure out what the next pixel is going to be. I need to use a little bit of trig to figure that out. Right, so when programming anything involving movement, right, we need trig, and I think that's a truth statement. All right, so an angle is a way of measuring direction. Again, this is just definitions, guys. Please forgive me. I'm not trying to dumb it too down for you guys, but we want to talk about this because we're going to build on all these little concepts here, and you can't do physics without any of this stuff. This is all required. Forget calculus. Without angles and geometry, right? Trig and geometry, you can't do physics, really. So again, if 2 people set off from the same point after they have both traveled 10 meters, They could be anything from 0 meters apart if they set off in the same direction to 20 meters apart if they set off in opposite directions. And the angle really makes a difference. The angle is the measurement of how different the two directions are. And when we think about directions in my mind, I'm thinking vectors. Okay, I know math again, Andrew. I'm so sorry. So when we think about these angles, and if you kind of take a bunch of different angles and you wrap a circle around them, as an example, right? All the angles in a circle added together add up to 360 degrees, right? If you think about that, right? So an example of this angle AB, is 90 degrees. And angle AC is greater than 90 degrees. And so is angle BC, as an example. We're going to be talking about these things like this over and over again. But notice the radius from the origin, let's call this point O to A, and O to B, and O to C is the same, right? Because that's the radius. That comes from the middle. So we're going to be talking about radius. Perimeter, right, as an example, again, like it says, is kind of from the center to its perimeter, to the perimeter around this. And the perimeter is the circumference of the circle, if you think about this. Okay? Diameter goes from one side of the circle to the other. All right? So those are kind of terminologies we're going to use. All right? And these are the radii that we're talking about. The counterclockwise angle between A and B, again, is 3/4 of the circle. Right? So from A to B, this counterclockwise. Sometimes we also call this anti-clockwise, right? Depending on who you speak to from which part of the world. Anti-clockwise. And I'm just looking to see who joined us because I want to make sure that we capture most people. All right? So pretty simple stuff so far. We're just going to continuously build. And generally when we talk about the angles between two lines, we usually mean the smallest angle. All right, and angles typically are measured in degrees, but when it comes to using our sine, cosine, and tangent, when we get to that whole trig part, we use radians. Okay, so in the previous iteration of this course, when we were talking about trig, and I asked you guys to figure out radians or the angles or triangles, complete the triangle might have been the exercise, as an example. Then I asked you to get a calculator, a non-graphing or graphing scientific calculator to do all the angle calculation that allowed you to change between degrees and radians. Okay, we won't be doing that this semester. So again, you can see that what we talked about before, that all these angles add up to 360 degrees, right? As an example, consider this little thing. Each of the angles, as an example, again, in this little arc here between 30 degrees and 48 degrees, this little small arc is 15 degrees, but all the arcs end up being a total of 360 degrees. For us, the most important thing is the right angle. The right angle is going to allow us to make many calculations when it comes to figuring out triangles much easier. All right? A right angle usually is 90 degrees. You guys should know about this. And it's also, if you think about this, a 90 degrees, right? And it says when two straight lines meet at right angles, they are called perpendicular. All right? So that's important to know. We're going to talk about what perpendicular to the curve as an example. So there are 4 right angles in a circle. And usually we kind of think about each of these pieces as quadrants. Whenever I think about quadrants, I think about Star Trek, the Delta Quadrant. But if you think about this, right, then on the top right corner here in X and Y, you have positive X and positive Y on the top right, negative X and positive Y on the top left, negative X and negative Y, and then positive X and negative Y. However, this is great in math. But one thing we always have to consider when we're moving things with physics is that a lot of times the y-axis is flipped, right? Because we draw a lot of times in a lot of frameworks from the top left corner of the screen to the bottom right corner of the screen, as opposed to the bottom left corner to the top right corner. So a lot of times we have to flip the y-axis. That's important. we can describe angles a lot of time in terms of their magnitude, right? So how big the angle is. A smaller than right angle is called acute. A larger one is obtuse, right? And an angle greater than half of the circle is called a reflex angle. All right, so again, just some names of angles. We're still in geometry. Once you know the radius of a circle, you almost know everything there is to know about it, because you can pretty much extrapolate every single point around the circle, right, by knowing its radius, if you think about it. We have a special thing in mathematics called pi, which is almost like a mathematical constant of the universe in some ways, 3.1415927. You should know at least that many digits off the top of your head if you're a game programmer, right? At the very least 3.14, which is going to give you some error, but at least it's going to give you a somewhat circular path if you need to make stuff work. A lot of times we don't want to use a whole bunch of digits with pi, because the more digits we use, especially for calculating pi every frame, it can increase the computational complexity of each frame calculation. And so we want to stay within a much simpler version of pi. And so for many times I recommend using a constant, a smaller constant that works for games. In math, we want to use as much precision as we can. In games, we want to fudge it and make sure that it works, right? So here's the area of a circle defined as pi r squared, which is kind of a famous equation, right? We want to find the total surface of a circle. Pi also turns up in things like circumference. I want to find the circumference of a circle, right? Again, I'm using 2 pi r, or if you think about this, it's twice the radius times pi. Or we can say pi d, which is pi times the diameter. 2r, 2 times the radius, is the diameter of a circle, right? So we can also call it 2 pi d. Radians. Like I mentioned before, typically what we do is we use angles and degrees when we talk about stuff. But a lot of our mathematical functions require radians. And if you think about this, 360 degrees is divided into 2 pi radians, right? So a single pi then represents 180 degrees, right? We're going to be talking about this in a bit. Sometimes we want to convert between radians and degrees, and I recommend to you in your frameworks that you're going to be using this semester, if I don't provide something with you, a util function, right, that as an example, that gives you radians to degrees, for example, a rad to deg function or a deg to rad function, then you need to put that in there for yourself. Why? You don't want to do the calculation, as an example, every frame. You want that pre-calculated for you. There's a special number that if you take, the calculation and put it in there, you can multiply by rad to deg or deg to rad, and you don't have to do that division or multiplication every frame. Okay, so, and it tells you here in these slides how to convert. I'm going to leave these slides for you to look at, converting from radians to degrees and from degrees to radians. Okay, let's talk about triangles a little bit. So again, as we mentioned earlier, we've talked about so far angles. So all the angles and everything else, right? Now we're going to be talking about triangles. And really when we think about a triangle is a figure made up of 3 points not lying on a straight line, okay, that are joined by 3 straight line segments. So we have 3 points somewhere, and they're not on the same on the same plane. That's what this is basically saying, right? When points are positioned in this manner, they are known as non-collinear. Non-collinear. They have to be non-collinear points. They're not on the same line. All right. Each point of the triangle is referred to as a vertex. This is important, and again, this is really super important because what's happening is here that we're going to be talking about vertices when we put together a mesh. Sorry. So you're saying that there are some noises from my mic? Sorry about that. I'm trying my best to keep it low. What I may use is NVIDIA Voice. There is an option for me to use NVIDIA Voice because I have an RTX 2060 in my little machine here. And maybe what I can do is I can shave off some of the pops and hisses. Right? We'll see if I can do that next time. All right. So types of triangles. So there's different ways of classifying triangles. And here's something to note, that when we start looking at triangles, I'm going to be looking at different parts of a triangle. For example, if I say a triangle ACB, right, or the angle ACB, we can also figure that C is, kind of the, the angle, the area, the vertex that we want the angle to look at the angle. So for example, gamma would be the angle that we're looking at, right? ACB, right? ACB are, in capital letters, are the vertices, right? A alpha or lowercase a, b, c are the sides of the triangle, all right? And alpha, beta, gamma, the Greek letters, are the angles inside of a triangle. Okay. Am I pre-ordering a 3080? I'd like to. 3070 looks pretty good too for the price. We'll see how it goes. So again, angles of a triangle always add up to be 180 degrees, right? If you think about this. So one demonstration of this is if you draw the same triangle 3 times as shown in this figure below, you can see that the angles alpha, beta, and gamma lie on a straight line, which means that the sum of these angles must be half of a circle or 180 degrees. So this is kind of proof that the angles inside of a triangle add up to 180 degrees. Why? Because if you look at alpha, beta, and gamma, these 3 angles right here, they add up to 180. And if these are the same angles here, because they're the exact same triangles, the theory goes that all triangles in interior angles of a triangle work out to be 180 degrees. And this is a lot of times what you use to prove out, kind of the angles that are inside of a triangle. And especially when we're trying to solve a triangle, which might be, on a test, it might be something I would normally ask you to do. All right, equilateral. So this is the simplest type of triangle, which is it has 3 equal sides and 3 equal angles. Given that the interior angles add up to about 180 degrees, exactly actually, then each angle should be 60 degrees. And you can see that we use a little mark here for all the sides that are the same in an equilateral triangle. This may not look exactly equilateral because of my drawing. This is just an image. But usually what it is these are the same size. So that's what these mean. And if you drew a triangle freehand, even if it didn't look equilateral, but you put in this little mark, we would know that's what you meant. An isosceles triangle has 2 equal sides, right? So this side and this side. And if sides A and B are equal, then the angles alpha and beta, these ones here, are also equal. Okay, so whatever that ends up being. And there's different angles because I could have different separation for the base of the triangle. So if the base of the triangle, as an example, is shorter, then these angles would be larger. If the separation between these 2 vertices here is wider, then these angles would be more acute. Okay? And finally, a scalene triangle is any other triangle, which, you don't have equal sides. That's possible as well. And when you make 3-dimensional meshes, you're going to see that in your 3D class this semester. You're going to have all of these different kinds of rectangles as you make up a 3-dimensional mesh. Okay? And sorry, you might be hearing my son. He's always screaming a lot when he's playing his video games. Woohoo! Yeah, he's playing. Especially when he plays D&D with me. I've been playing D&D with him lately, and he gets super excited when we're playing D&D. Okay, let's get back. Right angle. So again, for us, one of the most important things, kind of angle, is the right angle, right? And the reason for this is because we can use right angle to calculate all kinds of things. So there are special names for the sides of a right angle. The 2 of the sides are called legs, and one side is called the hypotenuse. All right. So the hypotenuse, which is this side, is across from the from the right angle. So this is your right angle denoted by this little square. And then this side here is the hypotenuse, or designated by H, of the triangle. Okay. Notice that we also have small a and small b on the other side here, right? And you have usually it's kind of in the opposite side of the angle. So if alpha is here and this is the capital A vertex, then normally you have the vertex here, which is capital A, alpha here, so a Greek letter representing the angle here, as well as a small letter a here across from the angle. That's how usually we do it. Okay? And the same thing for B. So if you notice that there's small b, and then here's capital B for the vertex, and beta for this particular angle. C is typically here, and it's across from the hypotenuse and the right angle. Okay? We know that alpha and beta, these two angles, must be 90 degrees because we only have 180 degrees inside of our angle interior. And since this angle right here, let's say angle gamma, has taken up 90 degrees of the 180, then it just says that alpha and beta must be the remaining 90. Okay? So that makes sense. There's a famous Greek mathematician, no relation to me, chances are, right? His name was Pythagoras. Actually, if there was a relation to me, I could claim, woohoo, wow, it's awesome. He's my relation. I don't know. Probably not, all right? But anyways, he kind of existed 569 to 494 BCE, so before the Common Era. And he's famous for having developed this theorem that relates the sides of the triangles. And Pythagorean Theorem is the main thing that we've used. You've already used this thing many times for AI calculations, for pathfinding, right? For things like Euclidean distance and that kind of stuff. It came from Pythagoras, right? The Pythagorean Theorem says that it works with right angles, and it says that they're easy to recognize and they crop up everywhere, right? And a second reason, because the importance of right angle triangles is that they have a number of useful properties, which we'll discuss in a second. And the third reason is that the following figure illustrates that any triangle can be split into two right-angled triangles by dropping in a perpendicular from one vertex to the opposite side. All right? So that's kind of really interesting, right? So again, some properties for us. So again, as mentioned earlier, right-angle triangles were studied extensively by Pythagoras, and Pythagorean theorem states that for right-angle triangles, right-angle triangle ABC, right, with the right angle at vertex C, and that's this right here, right? A squared plus B squared is equal to C squared. And this is a famous equation, and you can see that C is equal to the square root of A squared plus B squared, and you never want to do this inside of a frame. That's for sure. Once we start doing square root calculations every frame, it becomes computationally expensive, and we can do things like use the difference of squares. So we want to use the squared distance instead of finding the distance between two objects. This thing here, C, is equal to A squared plus B squared. If you think about it, it gives us the magnitude of the side. So if I go back to here for vectors, right? If I want to find the magnitude or the distance between A and B, that's what I'm figuring out, right? I want to figure out that C, right, is the square root of A squared plus B squared. So it's very interesting that that is the case, all right? It's used for distance calculations a lot of times. Triples. This is really interesting. These are also called, to me, magic triangles. I like these magic triangles, and you're going to see them all over the place. There's an infinite number of these, apparently, right? And you need a right angle, but here's one famous one, a 3-4-5 triangle, right? 3-4-5 triangle. And there are many other ones like this. Pythagorean triples is what they're called. 3-4-5, 5-12-13, 7-24-25, 8-15-17, and so on. Obviously, I don't expect you to remember anything beyond maybe 3-4-5. That might be a nice one to remember. And 1-1 root 2, which is also a very popular one. 1-1 root 2, right? So which is not written here. So those are Pythagorean triples, are also called magic triangles. Okay, and here are some examples. There's that 1, 1, root 2. Once you know some of these things, or 1, 2, root 3, that's another really common one. If 1, 1, root 2, you know that these two angles are 45 degrees. Immediately, if you can recognize this as a relationship of 1, 1, root 2, and again, as long as you keep the same ratio of side length. So if this is 2, 2, 2, root 2, right, as an example, or 3, 3, 3, root 2, it's always 45 degrees. Okay? And the same thing with 1, 2, root 3. If you keep the same ratio of sides, you know that this angle is going to be 30 degrees, and this angle here is going to be 60 degrees, and of course, the corners are going to be 90s. Okay, so that's magic triangles. All right. Also, we want to try and find the slope of a line, right, as an example, or A over B. Sometimes we also call this rise over run, or a gradient, right? A over B. And we can find the slope. It's a ratio of rise over run, or y over x, typically is what we do. So here's the y-axis, and here's the x-axis. So if I have some kind of vector, x, y, then I can kind of take the y-axis and divide it by the x-axis, and I can get the slope of the line. And when I have the slope of the line, then with some math, I can figure out the angle of, that separates of that vector relative to the origin. Okay, that's what it does. So for any right-angled triangle with a leg parallel to the y-axis, as an example, and a leg parallel to the x-axis, the gradient or slope of that hypotenuse is equal to A over B, okay, which is what we talked about. And once we have that, it's useful because we can create a relationship, as an example, between sine and cosine. One thing I want you to remember in this semester is whenever we talk about, for the most part, when we talk about things running across the y-axis, I want you to think in your head, sine. All right? If it's on the y-axis, we're going to use some kind of sine law or sine of something. All right? If I'm running across the x-axis for that component, a lot of times it's going to be cosine. And one of the questions I always have is, how do you figure out sine and cosine? And here's a question for you. Do you know how to figure it out from the top of your head? If I wanted to remember sine and cosine from the top of my head, how would I do such a thing? And for that, what I recommend is drawing it out. So let's, kind of maybe draw some axes here, roughly. So I take some axes and let's draw the, here's the y-axis and here's the x-axis. There we go. And I want to think about how sine and cosine work, right? And whenever we think about sine, we think about the sine wave, right? So for sine, I'm see if I can do this with my little tools here. We start at the origin, we go up, right? And then what happens is we come back down, right, to something that goes like this, and then we keep going, right? And then we come back up on the other side. That is your sine wave. Okay, let's think about that for a second. So if this is your sine wave, then can we not detect what this is? Well, here's 0. So a sine of 0, right, as an example, is just 0, right? So let's think about this. We have x-axis here, and I'm just going to make these points come up to this, okay? And so we can figure this out. So here's a mark here, there's a mark here, there's a mark here, there's a mark here, and there's a mark here. Okay, so those are the places where the sine wave would kind of interject, all right? So think about this. Where x is equal to some value, and where where y, right, is equal to 1, let's say when y is equal to 1, what's x, right? You got to think about what that is. Where x is equal to 0, then y is equal to 1, right? So now you're starting to think about what this represents. And if this represents pi, right? Because remember, if this represents an entire circle from here, as an example, all the way to here, so from this point here, all the way to this point over here, that is the entire circle. Then from here to here, this whole place here, this is really pi, all right? So this is pi, right? And this means this is half pi. That's what this represents, right? And this is 1 pi and a half, so 1 and 1/2 pi, or you can also call this 3 quarters pi, 3 halves pi, and this would be 2 pi, okay? So that's kind of like how we go in terms of radians, all right? So this is the angles that we're talking about here, right? So if I want to figure out sine when I want to figure out sine of when x is 1, then y is 1. When x is 0, then y is 1. When x is 2, then y is 0, as an example. And that's how you can remember kind of sine wave, right? Cosine is the same, except instead of starting from the origin, it's shifted to the left. All right, this whole thing here is shifted to the left, right? So cosine starts here at 1. So where x is 0, y is 1 for cosine. So if I was going to draw a cosine, let's see if we can draw in a different color. Let's say we'll draw it with blue color. All right, how about that? Blue. And let's pick the same thing. So we're going to start here this time, right? So here we start, and we're going to draw it so that it kind of hits this part right here. And then it's going to come back up, right? And you can see that it's kind of offset so that it hits the origin kind of offset with everything else. And sorry for my drawing. But then it goes on this side and does the same thing. So it's symmetrical, right? As we come down, and it goes up to this part over here, right? So this is kind of how cosine looks. So if you think about this, look, it has several of the same marks, right? So let's go back to black for a second, right? Here's black. So we have another intercept here. There's an intercept there. There's an intercept here. There's an intercept here, right? Here's where it intercepts. And there's an intercept over here. Okay. So let's think about this now, right? When, for cosine, when x is 0, right, then y is 1. It's different. It's kind of opposite of sine, right? When x is 0, y is 0, right, for sine. But when x is 0 for cosine, y is 1. When x is 1, then y is 0, right? And so on. You can figure these different places out by doing the same thing. When x is 2, then y is -1. And so on. And you can kind of map out all these parts of cosine. And that's how you remember how to do cosine. Again, from a pi and so on, this is 0 pi up here, right? This would be half pi. This is pi down here. And this is, 1.5 pi and so on. Okay, same idea. There's a great mapping tool that I recommend for this job. And let's see if I can get to it. And that tool is Desmos. And I put the link inside of your up on Blackboard for you. If you go to the Desmos Calculator and you want to calculate anything, for example, let's say I want to find the cosine of y, right, or the cosine of 5 as an example, and I want to map that out, it'll actually figure this out for you. It can also figure out some really cool equations. Like for example, where y is equal to, if I say y is equal to x. There's a linear kind of equation. Y is equal to x plus y, or x plus 1. Or maybe I want to find x squared, right? This is what we're going to use later on. If I do x squared, you can see that there is an equation of a line. We can talk about lines in a second. Or x squared plus 1. Notice when I add 1 to it, then it shifts everything up. And if I subtract 1 from it, then it shifts everything down, right? So that's kind of something. So if I say x squared minus a cos of x, right, as an example, or x squared minus the cos of 5, right, you can actually do all these equations for yourself right here, right? Or if I want to use another thing like tangent, I can literally just go in here and try it out. So try out Desmos, right? Desmos is a great little tool. We're going to use it later on today. All right, so we talked about this idea of rise over run, cosine and sine. And like it says here, the way to remember things is if you want to calculate tangent, you know that it's sine over cosine. And really, if you think about tangent, is related to our slope. right? Because sine of x over sine or cos of x, it gives us a ratio that determines our gradient, with respect to x. Okay, and we talked about these things, tan, cosine, and sine. These are the the examples. When we talk about trig, we also talk about trigonometric identities. And now you're going to ask me, how important is it for you guys to know trig identities? In previous iterations of this course, I could say super important because I would test you on them, right? But as an example, it's not going to be super important for this course. I just want you to know that there's trigonometric identities that allow us to create almost like relationships with sine and cosine. A good example of this is sine squared x. Sine squared x plus cos squared x is equal to 1, right? And again, one thing to note is that sine squared x is really a shorthand for the square, the square of sine x. So this is like saying this. Okay, it's important because when you look at this, you'll be like, wait, am I squaring? How can I square the sine? But it's different than sine of x squared. That's a different identity, right? It's a different thing altogether, right? Than sine squared x, all right? There's other identities here that are very common as well. Sine x plus y is equal to sine x cos y plus cos x sine y. And same thing with cos x plus y. I always remember, like, whenever I do a cosine anything, there's a negative sign somewhere. Whenever I deal with cos. So if I'm like cos x plus y, then I know that cos x plus y is cos x cos y minus, there's the minus, sine x sine y, right? So there's some identities. I'm not going to go through all of them. I just want you to know that there's relationships that we found in nature, and this is what mathematicians have done. They've looked at ways, shorthands, or quick, if you will, refactorings that we found out, so we can simplify the relationships that we see in the real world. Okay? And there's also inverse trigonometric functions. For example, the arcsine and the arccos, or the atan or arctangent. Guys, we use atan2 functionality so much in gaming, it's not funny, right? We use arctangent to find usually the resulting angle. A lot of times is what we do. I want to find the resulting angle, but when I have all the other the information, I can use arctangent for this. One important rule is the sine rule, right? So, for example, if I want to solve a triangle, and there's some examples in the back of the PowerPoint that ask you to solve a triangle. If we've been given all the information for a triangle, let's say, for example, I've been given 3 pieces of the information of a triangle, then I can solve the remainder of the triangle. Example, if I have A, which is the length of a side, and its opposite angle, okay, and if I have another angle in the triangle, we know that the third angle automatically is going to be alpha, beta, and gamma have to add up to 180 degrees. I have enough information a lot of times to figure out B, if I have A and 2 of the angles, right? And I can figure out the rest. I can solve the triangle by knowing part of the information because we know some things about the triangle. We can also use the cosine rule. A lot of times we don't have all the information, or the information is presented to us a little differently. And if you notice, it kind of is an extension of Pythagorean Theorem, where we can say that, well, a squared is equal to b squared plus c squared. These things are rearranged, by the way. Normally, it's c squared is equal to a squared plus b squared. But in here, it's the opposite. And then minus 2bc cos alpha, you can, again, use this sine law or cosine law, which is slightly more complicated, to also solve a triangle, which is what we're talking about here, how to solve a triangle. If I want to find the area of a triangle, here's the area of a triangle here, where we have these vertices, A, B, C, and I want to find the area of a triangle. How do we do that? It really depends on the measurements that we know, right? So using this method, we can, if I can fill in all the numbers that I know, then I can just use a triangle's area is 1/2 base times height. So then if I could figure out the triangle area for this side, then I can figure out the triangle area for this side if I know all the details. 1/2 base times height. Base is this. Height is this. So if this was the base, right, then it would be difficult to figure out. But this is for a right angle triangle, right? This may have started out as a non-right angle triangle, but I've dropped a perpendicular line in here, right? So once I've dropped the perpendicular line and I can figure out the distance between B and P, the perpendicular, man, I can figure out the rest of the triangle. And that's how we would do it. One thing to also note is whenever we want to figure out, we have a couple of pieces of information, and instead of using the sine or cosine rule, we can use Sohcahtoa, or Sohcahtoa, which is like I like to say, right? So we have, you know, if I want to figure out x, as an example, the sine of x, right? So I want to find x, but I have the opposite of x, this angle, this side, as well as the hypotenuse. Then I can say opposite over hypotenuse, which is the sine of x is equal to the opposite over the hypotenuse, or the so part, right? And once we have that, we know that the sine of x is this, right? So if I want to find the angle, it's the arc sine, right? The arc sine would be the ratio of opposite over hypotenuse, okay? The sine of the x is equal to the ratio, right? And I want to find the arc sine by plugging in that number into that function. And then I could find the angle. Once I've got this angle, well, guess what? Now we're into sine law, right, where I can kind of figure out the other sides and all that stuff. I can do Sohcahtoa multiple times until I figure everything out. We also know that once I figure out this angle, that this must be 90 degrees, so we can figure out what the other angle is just by taking this angle, adding it to this angle, and subtracting it from 180, right? So it's pretty simple, okay? All right, in the back of this PowerPoint, right, as an example, I may ask you to do some homework, and this is for your practice from an understanding perspective. There's no marks associated with this right now. But what I'd like you to do, and then what Spencer might do with you next week, is, again, is physically try and map this out with something like SDL, right? Remember, you can produce points, no problem with SDL. You can create mathing or plotting functionality with SDL, no problem, because you're just actually showing a dot on the screen, right? So here, you can definitely graph this out, but let's use a tool like Desmos. So x squared plus 4x minus 4. Let's try this out. So if I was going to use Desmos, then I just plug it in, right? So x squared, you know. So let's try this out. X squared, you put in the caret for up, so x squared. Let's do this properly. Where's the caret? There it is. X squared. Oh, man. Right? And then kind of use your arrow keys, minus 4x, if I'm not wrong, minus 4. Right? So let's do that out. So now notice that I'm going to get a series of points. So if I use Desmos, that's kind of the easier way to do it, right? And sorry, if you press both left and mouse buttons at the same time on the graph, if you're in Desmos, you can kind of move this thing around a little bit for yourself. But notice that one thing you can do is, if I concentrate on the line, if I click anywhere on the line in Desmos, it tells me the x and y coordinates of that of the graph. So why do I care so much about this anyway? Why do I care about formula? Guys, this is a path, right? If I have a path like this, I can do things like enemy movement, right? This could also be a motion graph. I, speed up, and then I slow down as I come here, and then I speed up again, right? Like a slowing down and then a speeding up, or a going backwards and then going forwards again. One of this is, it can be used to describe a motion, and it can be used to describe, some kind of path for an enemy, as an example. So really, really simple. So x squared minus 4x minus 4, right? One thing that we learned in calculus, which we don't have a chance to do here in physics, what calculus would do is say that we would have the position graph here. If this was the position graph, then how would I be able to figure out acceleration, right? So acceleration then could be described as the derivative, or sorry, the velocity could be described as the derivative of the position graph. And I'm not going to go into the derivative formula, but really it's just -4, right? So that's the derivative. And if you think about that, that's the velocity of, that describes the velocity, it's a linear velocity, of your graph. And if you think about this, the acceleration then is just, because we're going to be talking about velocity and acceleration, the acceleration is just the derivative of the velocity, the second derivative, if you will, of the position graph. Without knowing calculus, I'm just going to tell you that it's equal to 1, right? Why is that? Because there is no acceleration. You can see that velocity is actually a straight line. And if there's no straight line, the definition of acceleration is the increase of velocity over time. There isn't an increase of velocity over time. In fact, the velocity is linear, which means it stays the same every single time. It doesn't change. So, and usually you can figure this out because a linear formula doesn't have any kind of square root, or it's not to the power of anything. There's nothing like that. It's literally just some kind of variable plus or minus some kind of constant, and then it's a linear graph, right? For example, if I just put x, you can see that that is a linear graph, right? Where y is equal to x, right? For every y, there's an x. If I said x minus 4 for every y, then x is -4 of whatever y is. Okay. So that is the way we figure out. So if we're going to figure this out by hand, we would substitute. So again, if I was to write this down, I would start substituting x's. So I would say, okay, what if x was 0? That's the first thing that I would do. So I would take this formula, right? And I would say, well, what if x was 0? So if x was 0, then x to the 2 would be also 0, right? Or, yeah, 4x would, this is times, by the way, 4 times 0, well, that would be 0. So 0 and 0. So therefore, when x is 0, y is -4, right? And that would be your first point. When x is 0, y is -4, okay? So that's another way. You can make a graph or a table of x and y coordinates. All right, so again, if I did that again, let's try that again. And let's substitute another thing for x. So this is where x is 0. Oops. F of x is 0. What about when f at 1, right? When f's at 1, then what happens to y? Well, now you're multiplying this by 1. So when f is at 1, or when y is 1, that's what this means, then, or sorry, when x is 1, then y is, y to 1 to the 1 to 1 is 1, 1 to the 1, 1 to the 2, I'm sorry, so that's 1 squared, plus 4 times 1, right? And this is all the same, eh? But you calculate this first. So, you know, it's bed mass, right? Brackets, exponents, division, multiplication, addition and subtraction, right? So then you know that this is 4 minus 4. So 4 minus 4 is 0. So then when x is 1, y is 1 in this case. And we can test this theory by going back to Desmos and taking a look at that. When x is 1, right, then y is 1, you know, kind of thing, right, on the graph. That's the idea behind it. So let's just get rid of this and get rid of this. So when x is 1, what happens when x is 1, right? And who came in? Did we get Spencer in yet? I don't know if he's going to come in today. But you can see the graph. So if you kind of graph it out, and if you say, well, here's x is 1, there's x is 1, well then it should be right here, right? If we calculated things correctly. Did we do the right calculation? When x is 1, 1 squared, and then minus 4 times 1, minus 4, right? And then minus 4. You're actually adding them together. Minus 4 and minus 4. I just added a wrong calculation there. Then it'd be when x is 1, y is actually 1 minus 8, which is minus 7. Let's see if that holds true, right? Well, look, here it is. When x is 1, y is minus 7. Okay? I didn't calculate it right because I did this plus here instead of, I'm using plus instead of a minus, right? If this was actually the other way around, if I had plus, let's do this graph, that one, that's a different graph. You can see that it's shifted over here, then I would be correct, right? Because when, here's what I was thinking, when x is 1, then y is 1, right? That's what I would say if I did the other way around. So if I go back to my equation, then I was right. When x is 1, y is 1. And this for this equation, okay? Let's do one more. So this is how you make your table. You just substitute values of x inside the function, right? It's easily done in computers, but if I want to substitute whatever value I want. So 2 times 2, 2 to the power of 2 is 4, and then plus 4 times 2 is 8, so 4 and 8 is 12, minus 4, it goes back to 8. So when x is 2, y is 8. Let's see if we can test that. When x is 2, y is 8. So we're way up here, look. Right, when x is 2, y is 8. So that's how you do your table of values. And once you've got your table of values, you can, and why do we care about this, guys? Why do we care about this as programmers, as game developers? We care about this because if I want to map what the next pixel is going to be, and I want to predict where it's going to be ahead of time, right? I want to be able to use a formula like this to figure, okay, I want my motion to follow this path. I want my enemy to follow this formula for position. Every frame, I want to sub in a number in there, right, for position. I want to increase the x-axis as an example, or the speed across the x-axis a certain value. Then I'm going to change my position across the y-axis at some other value. There's a relationship between x and y is what I'm seeing here in this graph. Okay, and we can use a table of values to predict where it's going to be next. There you go. I like that, Kira. Perfect. Let me just get rid of these. We don't need these right now. All right, so this is some examples. I want you to try and do some of these examples on your own. Okay, and I'm not going to go do all of these because I expect you to kind of practice. We can go over them again next week during lecture, or you can ask Spencer to go over them with you. Okay, how about this one? So it says by plotting points, and we can confirm with Desmos this time. Okay, so this is a different thing. Again, this is just giving you practice on basic algebra and substitution. So again, I substitute values of x. I plug in a value for the parameter x of the function f, right? And the function f represents y. F of x is equal to y, or y is equal to f of x, right? We can complete the equation by saying that. We can say that this is equal to y, right? So that is the difference. So where y is some relationship of x, right? And that's what we want to talk about, right? So if that's true, and if we plug in, let's say, a value of 0 again, 0 plus 3, okay, so we're using BEDMAS, 3 to the exponent 2, so 3 to the power of 3 is 3 times 3 times 3. 3 times 3 is 9 times 3 is 27. Minus 2 multiplied by that is minus 54. Minus 54 plus 5, you're going to subtract 5 from 54. That's minus 49. So when x is 0, y is 49. That's your first point. And you keep doing that over and over and over again. Okay? Yes, you could definitely do that. But I want you to think about this. When we plug in values of x, then we're going to get values of y. That's what this means. Okay? And as we go forward, you're going to see other things. Okay, find the measure of each marked angle in the figure. Okay? How would we figure this out? If this one is a right angle, we know this is a right angle triangle, what approach would you use to figure out the angle x? Right? What is the angle x? If there's 2x here, and there's 3x here, and this has to be 90 degrees, then what is this? Very good. And Vincent has a solution. 2x plus 3x then is equal to 90. And if we were to use that, let's just use that as a thing, right? That's equal to 5x is equal to 90, where x is equal to 90 divided by 5. 90 divided by 5 is? Because you're going to solve for x, right? So 2x plus 3x is equal to 90, so that's equal to 18 degrees. That makes sense. So 3 times 18, right? And then 2 times 18, right? That's the angle. How about here? Same idea. But instead of 90, it's equal to 180. So 7x plus 2x, we know that adding these two angles together is going to give us 180 degrees. So 7x plus 2x is equal to 180, or 9x is equal to 180, which means if we're solving for x, we're going to say x is equal to 180 divided by 9, right? And there you go. So that makes sense, right? Vincent is asking, is it worth investing into an RTX 2070 right now? No. Yeah, I would say, again, hold off. Not related to what we're talking about, but that's okay, right? Okay, last one, and then I'll leave the rest for you. There's going to be some pages that I want you to think about and do. Well, I'm just going to go over them, but I want you to see if you can solve these things. They're very simple, but using the stuff that we talked about in the PowerPoint, you should be able to look at these and trying to figure out stuff. And this is for testing purposes only. In fact, calculus, if any way, is what we want to use for testing our physics. Make sure that the velocity is correct. Make sure that the acceleration makes sense, and so on. Okay? All right, so let's think about this. Sine, cosine, and tangent. We want to have this. We know this stuff, right? If I wanted to solve the triangle, right, it says find sine, cosine, and tangent values for the angles alpha, beta inside of this figure, right? Well, what I'd want to find is what is alpha, what is beta, and I can use Sohcahtoa for this. If you want to, you can use Sine Rule, because we have enough information to use the Sine Rule, where A alpha, as an example, A over sine of A, right? So A over sine of A is equal to B over sine of B. You have a lot of this information, right? So you can try and figure this out. You also know this, the hypotenuse, which is very helpful. So you can also use, which is equal to C over sine of C, and you know this angle is 90 degrees, so you're definitely going to use one of the equations. The ratios is going to be C over sine of C, or it's going to be the other one, C over sine of C, C over sine of 90. And again, if we're looking at sine of 90, what's a sine of 90 degrees? Well, if you want to look at it, if this is sine, right, and up to here is 180, then sine of 90 degrees is half pi. If we're looking at this, because this is 90, 180, 270, and 360. So sine of 90 is this right here, right? Sine of 90, right? Those are easy ones. Sine of 90. Cosine of, if I said cosine of 90, well, that would be 0, right? Cosine of, if you go further, right? So what is this angle here? So right here. So you notice that it starts here, it goes here, and it goes here. So cosine of 180 is pi, and so on. Right? That's how you figure those things out. You don't have to use a calculator for that. So once we have this information, we can solve the triangle, right? And you can use lots of ways. I see some stuff here. Tangent is equal to opposite over adjacent, and so on. Lots of different ways of doing this kind of stuff, and you're going to find all the angles to solve your triangle. Guys, solving a triangle for us is a key testing, quality. We should be able to look at a triangle and go, okay, well, do these angles make sense with the information that we're plugging into this triangle, as an example. And if it doesn't make sense, something is wrong. And we should be able to look at a triangle and figure that out, as an example. And why a triangle? Because I can figure out, as an example, if I want to go from A to B, really, it's something along the x-axis and something along the y-axis. There's the the x component and the y component. If I have this as the x component and I have this as the y component, I can figure out the length by using Pythagorean Theorem. And I can figure out the length in pixels between A and B, as an example, which is what I want to do every frame. Next frame, the next frame, the next frame. That means I can shoot a bullet in any direction this way. It's pretty simple. All right, the rest is for you. Please solve the triangles. And this is something else. Some other problem questions which messes people up. You're going to get some problem questions in class. I might give you some quizzes too, right? So here's something. The angle of elevation from a point on the ground 15.5 meters from the base of a tree to the top of the tree is 60.4 degrees. Find the height of the tree. What the heck am I asking for here? How would you break this down, this idea, before we end for the day? And then I'll leave the last one for you. So the angle of elevation from the point on the ground 15.5 meters from the base of a tree. All right, well, let's draw this out. So let's make a new graph. And if I drew the tree, let's draw the tree straight, because our trees in our life are all straight trees. There's no trees that are not straight, okay? So this is a tree, and it says a point on the ground 15.5 meters from the base of a tree. Okay. And we can label that. We can start labeling it 15.5 meters. Okay, this is what I would start doing, right? So there's my point on the ground, 15.5 meters. Let's put some values here. So this is A, right? Here's A. And then we'll put in B. Actually, if we do this right, let me undo that. Let me undo that. What we should do is label it correctly. A, and again, I don't know how tall the tree is, right? B should be here. Look at that, guys. And C, this is what we're starting to do, figuring stuff out, right? With the things we've known. We know that this angle here, what it is, without anyone telling us anything, right? If you think about it, okay, good. If you think about it, this angle right here, we know is 90 degrees, right? We know this is the truth, okay? So if we know this is 90 degrees, oh man, and we have one angle and one side, right? We have a lot of information already about this triangle, right? That we're looking at here, because it says to the top of the tree, the angle from the point of the base of the tree to the top of the tree is 60.4 degrees. Okay. So from this point here to this point here is 60.4 degrees. Just the way I've drawn it. Okay? Let's put that in there. So 60.4. I'm not going to put degrees. I don't think I have a degrees here that I can easily slap in there without a little circle. And let's make it so that it is smaller. Okay, 60.4. And we can make a little arc. When you draw your stuff, you can totally do this kind of stuff, right? So let's make a little arc that goes from here to there. Okay. So now I know some information. I would label this one beta. We'll just use a. We don't have beta, but we'll use B. Right? We shouldn't. We can use. This is actually B, right? And if we start labeling it, we can say that this is C, or the hypotenuse. This is the hypotenuse. Okay. And we can also label this as A. Let's label A. So this is A. Right? A is equal to 15.5 meters. B, we don't know. H, right, is the hypotenuse. We know this angle is 60.4 degrees. And this angle would be beta. We know what gamma is. We don't want to know what alpha is. We have enough information to solve the triangle. Okay? So pretty simple. And we're looking for, what is it looking for? Find the height. That means we need to know B. That's what we're looking for. We're looking for B, this one. Okay, the height of the tree. We don't know how tall this is, but we have this information. We can solve the triangle. Okay? So this is the first thing you do, guys. The first thing we always do is, can you visualize it? And if you can visualize it and you can draw it, it goes a long way to solving the problem. That's what we're going to do here in physics. We're going to solve the problems, okay, over and over again. All right. Questions around this? Any questions around the stuff we've talked about? Awesome. Remember that there's going to be some portion on the test that you may get, or a quiz, that asks you for some of this stuff, right? Because you have full access online, then yes, you can certainly go up and type it in and whatever, but you still know how to solve that problem. You still need to know how to do this. If I give you a problem, sure, you can figure it out by plugging in values that you know up online somewhere, like on Khan Academy or something else. There's a bunch of tools that you can plug in to figure stuff out. No problem, right? But coming up with this is what I'm going to ask you to do. All right? Symbol Lab is amazing. Yes, Symbol Lab is amazing. They can help you do almost everything, right? So yes, Windows character map. I'm sorry, Kira, I'm just not fast enough. Thank you. Wolfram Alpha. Any questions at all around the stuff that we've talked about today? Because this is your basis of the stuff that I want you to know. You should know about these things we talked about. And remember that you will be tested on them. So things around, Pythagorean Theorem. And that means that there's going to be potentially on your midterm test some questions around, or true and false multiple choice questions around how to figure this stuff out. It's going to be okay, guys. You can figure it out by using your tools online. Right, but the idea, the concept behind how this works is the important piece. Okay, guys, that's it for me this week. I'm going to stop recording now, and I'm going to take questions.